so this is a problem, an example problem I'm going to do from chapter 13, which talks about gravity. In this case, we have a rocket, which we're launching from the surface of the Earth. So you can think of it like this. Here's the Earth. So it's launching, it already is at the radius of the Earth. It launches upward. When it gets to a point 200 kilometers above the surface of the Earth, its engine shut off and it has a velocity going outward from them. The initial velocity at that point is 2.3 kilometers per second. What we want to try to figure out is how far up this rocket goes before it falls back down to the Earth. So what we want to get here is the maximum height, h, above the surface of the Earth. And the easiest way to do this, in fact the only way that we can do this in this class, is to do this as an energy problem. Conservation of energy. So we're going to do energy initial is equal to energy final. So at this point right here, what energies does it have? Well, it has 1/2 mv initial squared, because it's got kinetic energy, it's going upward. It also has gravitational potential, but remember, gravitational potential is minus g mass of the Earth times the mass of the rock times the r. But remember, r is this total distance here, how far it is from the center of mass. So what I'm going to place r with is re plus the initial height. We're going to call this d, or we're going to say d is equal to our 200 kilometers, where the re is the radius of the Earth. So that's its initial height. Right? And then over here, when it gets up to its top position up here, its velocity is going to be 0. That's where it stops and falls back. So there's no kinetic energy, we only have gravitational potential. So this becomes minus g me over m over re plus h. Notice again we're doing it this way because we want to solve for h, the height above the surface of the Earth. You could have called this one variable and this one variable and then at the end subtract it off. That's okay. I like to do it this way because it makes it clearer, but you can do it the other way as well. And so what we want to do is we want to solve for h. Okay? Notice that if we divide through by little m, the mass of the rocket doesn't matter. It goes away. Okay? And so we're going to multiply both sides by re plus h. So when we do that, we're going to get re plus h times, see those will cancel there, right? Times this, well the m goes, so this just becomes v initial squared over 2 minus g me over re plus d. And this is going to be equal to minus g me over on the side. Alright, now we're going to solve this for h, right? So the easiest thing to do is we divide by this whole amount here. So this becomes re plus h is equal to negative g me over the initial squared over 2 minus g me over the radius of the Earth plus d. So I've just divided both sides by this term right here to get this by itself. We want to solve for h, so now we just subtract re, and so we can say that h is equal to minus g me over v initial squared over 2 minus g me over the radius of the Earth plus d, all that minus re, the radius of the Earth. There, now we got it in terms of h. You could do some simplifying, get rid of the complex fraction, but in this case they want a number. So the easiest thing to do at this point is just to plug it all in and let your calculator sort all that out. So remember, you can look up the values, but g, this is going to be minus, and g is 6.67 times 10 to the minus 11. That's just a constant. The mass of the Earth is a constant, that's 5.98 times 10 to the 24th kilograms. all this goes over here, but we got to make sure we're in MKS units. So our initial velocity is 2.3 kilometers per second. Well, we got to put that in terms of meters, so that's actually 2,300 meters per second. That's squared over 2 minus 6.67 times 10 to the minus 11th times 5.98 times 10 to the 24th, all over the radius of the Earth, which is 6.37 times 10 to the 6th. That's in meters. Plus the distance we got was 200 kilometers, but remember that has to be in meters. So we multiply that by 1,000, that becomes 200,000. All that minus 6.37 times 10 to the 6. Now you just have to be real careful when you put this in your calculator, because if you don't put it in right, you're going to get the wrong answer, and you've got to put the scientific notation in there properly too. But if you do this all right, get the height that the rocket goes to is 6.870 kilometers, or 6,870 kilometers. Or if you did it in meters, sorry. Looked at the wrong answer there. That is the total height, but once you subtract off, that would be what it is before you subtract off the radius of the Earth. Once you subtract off the radius of the Earth, you get 500,000 meters, or 500 kilometers. So essentially, it has enough energy to go from 200 kilometers up to 500 kilometers before it falls back down to the surface of the Earth. Basically, it's an energy problem just like we were doing in the previous chapters. The only thing you have to do different is your gravitational potential is now this. You can't use mgh for your gravitational potential, lower g. You have to use minus gmm over r, and r is always going from the center of mass of the object. All right, that's how you do that kind of problem.